LOC 495. Yeah, this is class 6. As I mentioned before, this Thursday class, I cannot make it work. So in order to kind of make up, I think I'm gonna make a video clip. So all the team, we're gonna have the workshop this Thursday night. So everybody actually bring your laptop or use your desktop somehow. All the team should work on your project floor framing design. So today I'm gonna kind of show step 1 to, let's say, the 10, how to start it, the ETAPS model to create, again, same as starting with the unit, but to complete the composite floor framing design. If we have some time, I'm gonna duplicate all the floors up to 40 story and run it, and we're gonna do the column load takedown. So all the floor loading should be added, accumulated, and then we should be able to calculate all the actual load for the columns. So if we have a little bit more time, I'm gonna just run the steel column design as well. So let's get started. So what you see now is just ETAPS, yeah, our latest versions. So I'm gonna just start with the file, new file, and since this is a US project, I'm gonna use user save the user default setting using Imperial. So when you open it, there is a quick template. For conveniency, so the typical floor height, we're gonna use 15, and we're gonna use 40 feet or 40 story tall. The grid, eventually we're gonna revise it, but we maybe can try to use it. So the column spacing in X direction, we're gonna use 30 feet. Number of grids, maybe try to 6 or 7. Let me see, 6 or 7 grids, 1, 2, 3. Okay, so I'm gonna start it Y direction 45. So but I need to adjust it because this is our building is not going to be everything is asymmetric, or column spacing should be slightly done on uniform. So I'm going to start open, and this is a grid system based upon the template, right? You make sure that all the plans, and here we most likely when we build a plan we using the plan view. So I'm gonna just maximize the plan view. So the default is top floor, but I'm gonna just move to the most bottom floor. If you want to go up and down, this arrow is you can move up and move down. When you move down, you see the elevation 0. When you click it, this is elevation, the story 1, elevation 15. So let's check the overall building story information right here in edit, and you can see that. So since we're using 40 stories, and we fill the 15th typical floor, and we type in the 40th floor, so the ETAPS is set it up building floor elevation up to 40 story, which is elevation 600, right? So I think this is set. And one thing that we for high-rise building, let me see, 1, 2, 3, 4, 5. Maybe we can try either. Okay, so this is something example. So here the grid, once we use a template, and then also you should be able to modify from the grid system, where when you click in modify grid, you see the X grid coordinate and Y grid coordinate. So see that I type 45, so they set it up. Every grid is spaced at 45, but I'm gonna make it something 75 here, 75 plus 45. Right, so I'm gonna adjust a little bit. So you see that the column grid A to Z is 30 feet spacing, and then Y direction I have 45 and 30, 45. So this is my grid system I'm gonna use, and I'm gonna start with something. Let's see, how can I start? Okay, so I'm gonna first of all draw the wall, but let's check the material default. We have a 50 grade 50 steel, concrete I think 4000. We're gonna just keep it for now. So I'm gonna draw the wall first on the plan view. Here, draw walls, right? When you click it, properties, they pick up the default. Let me just draw. Eventually, our wall is, I think, it needs a little bit more. But let's see. For this exercise, I'm gonna draw the wall like this. You know what? Let's extend up to here. Okay, so I drew the wall. Let me just put it 3D. Because I drew the wall at the story level 1, you see that all the wall is located between base and first floor, right? Okay, so this is the wall. Obviously, if you want to this checkbox doesn't work. So I'm gonna turn on the section property name. So default is wall 1. I think its default is here. You can see define the wall section. Wall 1 is 4000 psi concrete and 12-inch concrete wall. All right. So this vertical wall, I just layout I drew it. We're gonna further revise it later. And then the second thing is we're gonna also draw the column. This case is we have default is auto selection lateral column. Yeah, let's use it. So I'm gonna just hover in among the intersection. I'm gonna draw the column. But you know that because it sometimes is kind of too much in a clicking. So since I know this is 30 feet spacing, I can just copy, right? Edit, replica. So in the extraction, 30 feet, 1, 2, 3, 4, 5. So I'm gonna copy 5. Oh, wait a minute. 5 and 30 feet. Let me just reselect here, there, 30 feet, 5 times, right? Okay, same thing that you can, if you know this, you select 1, 2, 3, 4, 5, 6, 100. So one time, 180 feet, I'm gonna copy. So I can copy the column. Just in case, I'm gonna save this file. And this is workshop. So workshop. Okay, so I'm gonna move a little faster because otherwise this file is gonna be humongous. Second, we're gonna draw the beams. But typically, I think our building we're gonna rely on this wall as a lateral load. All column and beam is gonna be gravity frame. So I'm gonna just assume everything. I'm gonna use auto selection, auto composite beam section property, and I'm gonna use a pin connection, right? So this graphic is a little sensitive. I'm gonna draw the beam like that. So since we pick up the pin, this checkbox, I'm gonna turn on the end moment and release. So you see that the beam has a simply supported connection, right? So you could just draw same by clicking, or I'm gonna just copy, replicate, same thing, 30 feet, 1, 2, 3, 4, 5, 6, 6 times, right? I can copy this. Also, now Y direction, I'm gonna draw 1, 2. Have to be careful slowly, because sometimes I see it pick wrong point. Oh boy, I think this mouse or this recording mode usually doesn't let me draw. Let me delete it. Okay, it's a little sensitive. That. Okay. Okay, so I draw it. Okay, I'm gonna click refresh. So this beam was added, all simply supported beam. Again, I'm gonna copy, replicate. Right, 1, 2, 3, 4, 5. 30 feet spacing, 5. All right, this is just about drawing the beams, right? How you draw and replicate is up to you. Oh, I missed this. I'm gonna copy, replicate. 180, one time in X direction. All right, so I'm gonna save it. So what you see this, you see it in 3D, all the vertical column, walls, and girders. All right, so now, so filler beams, we're gonna draw it, but since we have all the grid set up, this is kind of great tool, pin, everything is 10 feet on center, as I mentioned it, slab. I'm gonna kind of draw the two beams so that we have a 10 feet spacing. So again, I'm gonna choose a composite beam section property and pin connections, and I can just easily click the bay, which is I love this, the ETABS features. And then I'm gonna click the refresh. So I assign all the section properties. I'm gonna save. All right, now we're gonna define the section properties for metal deck slab, right? Define, I think default metal deck section here, 3-inch metal deck, but we're gonna use this time 4.5 meter. So with normal weight concrete is support 2-hour fire rating without fireproofing material underside the metal deck, or you can use 3.25 lightweight concrete. But now I'm gonna use normal weight concrete, so I'm gonna use 4.5 inches metal concrete topping. All right, so I'm gonna click this. I can draw the slab by using this draw floor option or draw rectangular option, right? So this is a metal deck. Now one thing is I'm gonna draw and see. Okay, default is local x is 0, means this is metal deck is spanning in x direction, right? If you put 90 degrees, and yes, metal deck is spanning in a north and south direction, right? So since this key, I don't know why, but this delete key doesn't work. All right, so I'm gonna put the 0, so our metal deck is spanning left and right, and click this nose and hold down and click it. So you see that metal deck is spanning left and right. And eventually the building has a little bit of need to be overhang, right? Because the slab cannot be stopped at the center of the beam. Usually you need a little bit of overhang. What you can do here, you could select this shell element, edit the shell, and here expansion and shrink shell. So I assume maybe, 24 inches. So I expand the slab and create the overhang by 2 feet, right? All right, so basically we finished the geometry. This is when you right click, you'll see the metal deck 1. We haven't done, assigned the floor loading yet. So what we're gonna do, we're gonna define the load patterns. Default, we have dead load, which is self-fade, which is good. We're gonna create the superimposed dead load. We're gonna add a superimposed dead load, but you make sure you don't include the one self-fade again, because self-fade should be only count at one time. Now construction live row, we're gonna edit. So here, construction live load. So we need 4 load patterns, right? Now we're gonna assign the load one by one. So Slab, and we're gonna assign, go to shell loading, uniform load. First one, that load is self-edge, so we don't have to edit anything. We're gonna assign the Composite dead load 20 psf in gravity direction, which means it's cover, ceiling, MEP, or the floor finish. So I assign. Again, either click it or previous select, live load. This time we're gonna assign 100 psf, right? And click again, construction live load. We're gonna assign 20 for now. So I assign all. Let me double check. Right click, select and right click. You see that STL 20, live load 100, construction live load 20. So we assign everything. So gravity, no geometry is done. Live loading was fully assigned. Next step, we're gonna set up the load combination. So in the load combination here, you can use default load combination. Because we are designing composite beam, we select this. So ETAP's gonna set up the load combination for you, right? So now the thing is we are ready to run. Okay, let's wait a little bit. Okay, this displacement doesn't mean anything. We need to use composite beam and always encourage you guys to actually go through all the composite beam design and then check the deflection. So this deflection displacement doesn't mean much. So first thing, what always you guys has to do, confirm your input modeling is correct. So we're gonna check the moment diagram due to the any load, uniform load. See that something going on here, right? This is now moment that we are expecting, right? And the shear force diagram, something is going on. Something is not properly assigned all. So let me double check. Gosh, this. So let's see. Something is missing. Maybe boundary elements might be not assigned. Interestingly, usually automatically assigned. Okay, here the column some boundary condition pin wasn't assigned. So I select all this, assign join, restrain, assign, join, restrain, and assign the pin. Usually when I draw the full framing and column down, usually they automatically assign the boundary condition, but I think this may be graphical some issue. Let me just create the this boundary condition symbol bigger. So go to options, graphic preference. Yes, make a little bit bigger. So graphically a little bigger. Okay, now I'm gonna rerun it and check the member forces, moment and shear diagram. Okay, I'm gonna put plan story 1 here, double check the moment diagram again. Okay, now all single curvature, that looks like right, because this is all pin connections. Shear force diagram should be same thing, similar to like this, right? So you should at least be able to check by hand too. This is very straightforward because 100 psf time, tributary width 10 feet, you could see that WL square of 8. That's an easy math. Everyone should continuously practice. All right, so it's time to run the composite beam design. Oh, this graphic is horrible. I'm gonna change to graphic mode to standard graphic. All right, so now since beam is all composite beam, let me see whether I can select all the beam member, right? and I'm gonna tell I'm interested in frame composite beam design. I assign the beam, and then I select all the beam. I'm gonna go to design, composite beam design. I think default typically okay. I'm gonna first of all run and see what I'm getting here. All right, so you could see this. I think ETAPs provide all sizes which workable. Let me just click one typical beam and check it. So this is acceptable design member sizes, right? You could see that as it goes down, the member size is bigger. That means they don't need actually, because it's big, they don't even camber, but lighter section you need a camber, right? And so this case is W21 by 50, need number of shear stud 38, which, and also need a 2 camber, right? 2-inch camber, which you end up with stress ratio 0.99. But this is not all the strength requirement. I think ETAPs go through all this ratio, strength check, deflection check, and show, I think, the worst case scenario here. But for the strength standpoint, you see the 0.914 is a stress kind of ratio. So as I mentioned before, composite beam design is actually go in 2 phases. One is during the construction phase, which concrete is not cured. It's a wet concrete. Steel beam should take care of all the wet of concrete weight, so that you could calculate this basically 1.2D, 1.6 live rod manually, or maybe have double check by hand. But also after concrete is cured, 1.2 that plus 1.6 live rod, you're gonna end up with this moment, keep it 714, right? This W21 by 50 with the number of stud 38, we're gonna have the bending capacity of 781. So this is ratio. All this is stiffness check is also, you could see this, you could see that all the ratio, and this is backup calculation. I want you to just go through a list, see. Some detail is maybe graduate level, but I think this is kind of conceptually you can easily understand. Composite action is depends on number of stud, how the concrete metal deck slab with the steel is how solidly glued together, right? The more and more the solidly the glued, they can achieve the more strong strength and more stiffness. So I want you to just take a look at it. Maybe something that the deflection, you should look into this. Let me see, either this diagram is okay. So live rod deflection here is set 0.96. Let me see, live rod deflection 0.97, a little bit off. But this seems like live rod deflection and 0.97, yeah, 0.97, right? I think this is the diagram and deflection, and you need to use STL live rod deflection. This is actually deflections based upon composite section properties. Let's say dead low deflection is 2.63, here 2.64, okay, 2.64, right? So this is very, due to the self-weight of the concrete, the only bare steel deflection. So here it show pre-composite deflection 2.64. Since this self-weight, the deflection is more than 3/4, ETAPs choose some camber, right? For this beam, they recommend 2-inch camber here, right? 2-inch camber here. So total deflection minus camber, obviously, you end up with 1.8. Without 2-inch camber, this is total deflection will be the 3.8. It should be greater than allowable, L over 240. So we're gonna just talk about it later. This is straightforward. The concept is very simple, but obviously the camber is quite, this case is useful, so that the ETAPS choose typically depends on the specification. No, it's bad. Override the camber. No, deflection criteria. Here, no, not here. Camber usually applies 75%, 70% up here. Let's double check. Composite beam, preference. Camber is, yes, apply 80% of dead load deflection, roughly, right? So go back to this, right? So 0.8 times Excel. 2.64, 0.8 times 2.64. So roughly 2.11. They choose 2 inches roughly. So here you see that camber 2 is about 80% of self-weight concrete weight. The steel beam deflection under the self-weight, they just recommend 2 inches, and then they go through all this deflection check. All right, so once you design here, I think this is the sizes temporarily they selected, right? One thing that you need to aware of it, typically beam and girder sizes. Usually girder we choose a little bit deeper than beam, so that we just cope. We need to cope the girder or the beams on the top side. If this 21 is framing into 21, you need to cope, right, top and bottom. So I think that may be adding some fabrication cost. So typically girder is deeper than beam is more compatible, the competitive cost saving. All right, just for this exercise, well, since we actually have some initial sizes, we need to override auto selection section with the current design section. So composite beam, go to verify all member paths, right? And click it and rerun the analysis, so that ETAPS is override all this current design section over the auto selection section property that initially we use it. So let me see. Yeah, this, okay. See that all the member sizes 21 by 50 was actually chosen, selected here, overridden, right? Okay, so I think you can just play around up to this level. This is up to composite beam. I think composite beam design, so the procedure is over. Oh, come on. Maybe because this bar, I cannot move. Okay. Okay. Now, what you can see, since once we finish it, we can just double check. Also, color actual force diagram, right? This is based upon gravity area. We already studied a few times. See that due to the self-weight, you see that 55 kips. This is based upon gravity area. You should be able to calculate by hand. If something simple, 100 live load is 100 PSF. So 100 PSF times gravity area, you can get the this column reaction. All right. So I think everybody should finish up to here.